Okay, welcome back, everybody. So now we have the Astropy lecture still with Axel, so I won't spend time introducing Axel again. Let's dive in.
Thanks a lot, Thomas. Okay, so for the second session this morning, we're going to take a look at the Astropy package. So on Wednesday, actually, Tamas already showed some motivation for the Astropy package, just in a single line. So it's a community Python library for astronomy. And going a few years back, the situation was really that there were like many packages around for things like sky coordinate transformation, for FITS-IO, for astronomical data tables, etc. And then at some point, on I think even probably on some mailing list, people got together and said, okay, maybe let's create just like a common package, a common core package for astronomy. And this was basically the birth of Astropy in 2012. Just on the general structure of the lecture. So again, I'm just going through the notebook. I will show you a bit of the functionality of Astropy. The recommendation would be just again to go with me through the individual cells, just execute those. Right, and I think for the Astropy lectures, we might have a bit more time on the exercises. So again, after each block, there will be an exercise, or actually multiple exercises. I've divided those into easy ones, advanced ones, and hard ones. I think we've seen from the poll by Tamas that there were still a lot of beginners in Astropy. In this case, just start with the easy exercise, maybe the advanced one. If you consider yourself already an advanced Astropy user, then you can directly start with the hard one, or you could solve the easy one and then you're done in a minute or two, and then just continue with the next one. For all the exercises, we also provide a solutions notebook, which is in the same folder. If you want to keep the fun of solving the exercise, then just take a look at it later. Again, the corresponding Slack channel is just the one for day 5, Friday 11th, and then Astropy. Again, I mean, if you have feedback or questions right now, just put them in the Slack. If you have feedback or questions after the course, you can either write me a mail or just use the repositories issue tracker to open an issue. Okay, I've already put the definition of Astropy, so it's a community Python library for astronomy, and there's a bit more detailed information here. So the Astropy project is not only this library, but it's actually community, and it's a community effort to develop this single core package for astronomy. But it also tries to foster the interoperability between Python astronomy packages in general. So the structure and concept of this is defined in the Astropy paper here. And then also, I think there was an update in 2018 on a more recent paper of Astropy. This was just this general thing that I noticed. I mean, many of these software packages that we provide have actually a way of citing it. For Astropy, it would be to cite one of these papers. The general recommendation would be that you just, for example, go to the website of the package you're looking at, and then here you can see you can find a link, acknowledge, and cite the use of Astropy, and then there's like the recommended way of how to acknowledge and cite the use of Astropy, either in a paper or in a slide, and then you can do this justice in your publication. Okay, in general, the Astropy package, just as SciPy, is structured into multiple submodules. And those submodules cover a broad range of functionality that is useful in your daily work. I've done a sub-selections of what I would consider like the most important ones, and let's say like the ones that I use, I don't know, 80% of my time. And those are typically Astropy units, and in particular the quantity class, which lets you do calculations together with units. Here I'm writing astronomical calculations, but strictly speaking, of course, it's not limited to astronomical use cases. Then there's the Astropy coordinates subpackage, and here in particular the classes sky coordinate and angle, and those help you to handle transformations between positions in the sky, different coordinate systems, and coordinate transformations in general. Then there is this Astropy tables package, which mostly defines this table class structure, which allows it to handle table-like structure, like catalogs, for example. Then there's also the support for this FITS format. I think FITS is like a very common data format in astronomy, and Astropy provides an API to read and write those FITS files. And then, if the time allows, there's also another useful package, which is the Astropy visualization, and specifically the WCS axis subpackage there, which helps you to plot astronomical sky image just using the normal Matplotlib API. In addition to this Astropy core package, there's actually an infrastructure of what are called Astropy affiliated packages. And those are really dedicated to very specific fields in astronomy and analysis tasks. For example, there's a package called Astroplan, which helps with observation planning. There is a package called Reproject, which helps with the reprojection of sky images. There's a package called Regions, which allows you to define regions on the sky and work with the regions. And then there's a package GammaPy, which implements gamma ray data analysis. And this is also what I'll present on Monday next week. There are many other affiliated packages. Here you can check the link. So here's like the full documentation of this. Again, if you're looking for specific functionality related to some astronomical problem that you want to solve, just take a look and see whether there's already a Python package or an Astropy affiliated package that does this for you. In general, just to conclude this comment here, there could also be your package. I don't know, maybe if you're already an advanced Python user and you've written a certain package to solve a specific problem, then you can actually propose your package to be an Astropy affiliated package, and then there's a procedure and a review phase that would allow to adopt this. In general, there are a few other resources that I like to link where you can learn about Astropy. One that is highly recommended is just learn.astropy.org. This is a webpage with a lot of tutorial material in addition. Then, of course, there's the Astropy documentation. I mean, this is always like a good place. Then there's also the associated Astropy tutorials repository. The content is basically the same as in this Learn Astropy one, but then you can actually take a look at the repository itself. Then there's some link that I found on the Astropy workshop, which was held at an AAS meeting. Then there's also the Stack project, which is provided by Space Telescope Science Institute, that has some tutorial notebooks for these typical IRAF analysis tasks. I also found a webinar on YouTube provided by the Astronomy Data and Computing Services. I think this might be also a good point. I mean, once you've gone through this lecture, I think there's probably not much more additional comment in this webinar. Okay, I think that's basically it. If you want to for the introduction, if you want to get help, there is an Astropy Slack channel as well that you can join. And I think all the resources are linked in on the website. You can use Twitter. There's a Facebook group as well, mail list and a Slack team, and the developer list. Okay, last comment on the introduction. So if you want to contribute to Astropy, there's also an entry point that you can take a look at, which gives you the entry point if you want to actually, I don't know, fix a bug in Astropy, something like this. And then you will get some instructions on how you can actually do this. Okay, let's start. I'm just starting here with the usual imports. So we're using again Matplotlib for the plotting, NumPy for the data structures, and then Astropy. And currently we're using, I think, very recent versions defined in the environment of the school. Okay, let's start with the unit and quantity handling. So this Astropy unit subpackage provides functions and classes to handle physical quantities with units. There is a convention to actually import the units as from Astropy, import units as U. You don't necessarily have to follow it, but I think you will see it in a lot of examples, and it's probably a good idea just to follow it this way. And here's just already one example how you can define now a quantity with a unit. So here we're defining a distance of 1 light year, and if we print it, then you can see that it does not only print the number, but it also prints the associated unit to it. Another way of creating this quantity object is just to rely on this general quantity object. And this general quantity object takes a lot of things. For example, it knows how to pass a string. And now if you print the distance here, then it's again a number with the associated unit, or if it was something else like this, then it knows how to parse this and recognizes this as a unit. Okay, what are the available units? So we've imported the subpackage as U dot, and then all the available units are then accessible via tab completion. So you type U dot, then you hit the tab key, and then you get a list of all the units which are available, and they're, in short, there's basically like everything. I don't know, atto arc minutes, atto arc seconds, counts, flux, hertz, Jansky, Kelvin, etc., angstrom, whatever. But I think like this interactive way is a good one to find. You can also just start typing. I don't know, for example, you might want to look at, I don't know, maybe you're interested in or looking for a certain unit. Let's start simple, like meter. Okay, so you could type ME, hit tab, and then you will see the tab completion, what's available there. Or you could just type MET and then hit tab, and then it already completes to meter. Okay, this is one way of instantiating those. This was just a single number. But of course, we can always work with arrays. I mean, this is what we're doing with NumPy all the time. And a way to instantiate an array with the unit is basically the same syntax, except that you have an array-like data structure before. So you pass, for example, using a list of values here, and then you multiply it just with a unit. Or you specify some NumPy array and you multiply it with the unit. And then if you print this, then it knows all the array values and it has the associated units. A few more details on how this is actually implemented. So you can now, once you have this distances object, you can actually access a data member called .value. And if you check what type this is, then you can see it's just a NumPy array. And this is actually might be useful in certain situations, because you might already be familiar, for example, with the NumPy array, with the NumPy API, and in general, Astropy quantity tries to mirror this API, but it's not necessarily true in all cases. But this is something that we can see later. So this is just really the plain NumPy array. Then there's a second data member that might be interesting, and this is just the .unit attribute of the distances object here, and this is just the units.core unit object. And this is basically already the core of this quantity structure, so it just bundles the NumPy array together with the unit. And this also means that in many ways it just behaves like a NumPy array, just with this attached unit. So for example, if you take the distances multiplied by 10, then it will just multiply each value in the array by 10, and it will keep the unit untouched. What's also nice is that basically many NumPy functions, I think by now probably almost all, will work as expected and return again a quantity object. So if you want to find the maximum of the distances, then you can just call into numpy.max, pass in the distances, and what you get back, as you can see here, is again a quantity object with the associated unit. The same works also for NumPy bean, for example. There are a few exceptions. One of those would, for example, be taking the logarithm of a quantity. There's, of course, the requirement that the value you take the logarithm from must be unitless. If not, as I'm showing here in this case, so if I'm trying to take the logarithm of 30 mega electron volts, then it will raise a unit conversion error for good reasons, of course. The way in this case to get around this is just to specify a unitless quantity. So for example, in this case, I could specify a reference energy, and then it's happy to take the logarithm of that. The most useful method on the quantity object is a method called to, distance.to, and this allows you to handle unit conversions. And this is basically what quantities is all about. So we've specified this distance in light years, and now we can actually just convert it to meters by giving the new unit here as a string. And then you can see, okay, like 1 light year already corresponds to this distance here in meters. Or the same, for example, we could convert to parsec, and then you can see that 1 light year corresponds to so many parsecs. What's also nice is that I've already mentioned the quantity object behaves in many ways like a normal NumPy array, and this also means you can do calculations with it and arithmetical expressions, and the quantity object will take care of the quantity handling. So for example, in this case, we can just divide the distance by 1 year to get the speed of light. That's of course how it is defined. And then we could convert it finally to kilometers per second. And in this example, then here, that's what you get. I think I'm just wondering about the value here. So above in the cell, I've changed the distance to this random value, this one here. So if I change this back, then you get actually like the correctly expected value. Okay, so here we are. Of course, but you can also just convert to, I don't know, some weird units. I don't know, you could convert the speed of light to angstrom per day. A good way is just, I don't know, to specify the units as a first guess, and then see whether it raises a unit error. And if it raises unit errors, then you can still check, for example, whether this unit is not available or something like this. But in many cases, you will be lucky, and the unit is just supported. I think in general, the most practical way of working with units is roughly the following. So you define your input data and your input quantities with units, then you do the computation, whatever you want to do, and you forget about the units. And then finally, when you want to take a look at the result, then you just convert to the desired units. And in most cases, for example, there's no need to do, let's say, like an intermediate unit conversion or something like this. Just as additional information, so if you take a look at the default units, and so we've done the computation year distance divided by 1 year. So the default unit here is then really like 1 light year divided by 1 year. So Astropy does not simplify anything by default, but that's why then you just finally do whatever you want with it and just say, okay, then I want to convert to kilometers per second. For standardized unit systems, such as the SI system or CGS, there's a convenience attribute on the quantity object that you can use. So you could just say, like, I want to have the speed of light in SI units, and then you can just access .SI. I think this is convenient in certain cases, and the same for the CGS system. Okay, a more advanced use of quantities are equivalencies. So typically in astronomy and other fields of physics, they're often measured in more practical units, which are just equivalent to another actual physical unit. And in Astropy units, this is handled with the concept of equivalencies. I think a very, very common use case is, of course, spectral units, where the spectral quantity can be measured as a wavelength, as a frequency, or even as an energy. And for this, Astropy has these built-in equivalencies here's an example. So we just define a frequency as hertz, and then we want to convert this to mega electron volts. And in case where we don't specify the equivalency here, this just fails and it raises a unit conversion error. But you can provide some context to the conversion with the providing the spectral equivalency here, which is defined in u dot spectral. And then, of course, the same works for wavelength as well. So you can just convert it then to picometers, for example. Another example where this might be useful is converting temperatures. So Celsius is not an absolute scale for temperature measurement. So in this case, we need to provide some context to convert it to Kelvin. And for this, there are these built-in temperature equivalencies. And with this, then you can actually convert the temperature given in Celsius or Fahrenheit or whatever to Kelvin. There's one, just to mention, I mean, there's one special case. So there are, of course, imperial units sometimes around, I don't know, like inches and foot, etc. Or in this case, like Fahrenheit. And there's a special syntax to make this work in Astropy. And this is this with u.imperial.enable. And then you can make those imperial units work. I think it was probably a wise choice by the Astropy people to not enable those by default. But you can have this this context manager here, which allows you to do this conversion here, for example, to convert to degree Fahrenheit. Okay, there's some miscellaneous things that are useful to know for Astropy units. So in addition to the units and quantities, there's also Astropy constants. And this implements very common physical constants that you might want to use in your work. For example, the speed of light is available as const.c. So we say from Astropy import constants as const. This is again just another convention that you might want to follow. And then you can access the constants, and they're available as quantities, and then you can convert them just to arbitrary units. So here's a link with a list of all available constants. So you can just click on the link and check out what's defined there. Another useful thing is this quantity input decorator, which is defined as u.quantity input. And this is just a way to make sure that the quantity that is passed into a certain method has an equivalent unit to what is defined in this quantity input. And this is a good way to prevent, for example, a usage error, or to prevent a colleague that uses this function to call it in an incorrect way. Here in this example, I'm just defining the black body function. And I want to make sure that the frequency that is passed in is somehow equivalent to Hertz, and the temperature is equivalent to Kelvin. And now if I do something incorrect here, then it raises already the units error and just says, okay, argument frequency to function black body must be in units convertible to Hertz. This can be useful just to provide like an input checking of the quantities that you pass into a method. Need to check the time. I think we can maybe quickly comment about this. I think this could be useful. There are often situations where you want to interface quantities with third-party code, and not all other packages, for example, SciPy or Matplotlib, understand quantities, of course, because it's an Astropy. Because it's unique to Astropy. For NumPy, this mostly works, but there are other packages, as I said, like SciPy or Matplotlib, where this does not work. In the case of Matplotlib, there's actually a nice convenience method, which is called quantity support, and you can import it from Astropy visualization. And this then lets Matplotlib understand quantities. So we can define the temperature here. We can define the array of frequencies that we want to evaluate the black body on. And then we can actually plot the shape of the method with quantity support. And the way this is used is with this context manager with the with statement. And then we can directly pass in the frequencies and the radians as quantities. And then you can see that it even then plots directly or labels the unit on the plot that you've plotted. There are a few situations where you have to actually strip off the unit. One example or little example I've shown here. So there's this NumPy log space method that lets you define. It's basically similar to linspace, but it does a logarithmic spacing of the binnings. And in this case, for example, we want to have a logarithmic spacing between 1 and 10 TeV. But in this case, the log 10 of, as we've seen above, of the energy does not work. And what we can do as a workaround is we can just access the value, so the plain NumPy array of the energy, the same here, and then finally we can just reattach the unit. And this is one way to work around this problem. So convert to well-defined units beforehand, do your computation, for example, in SciPy, and then reattach the units later. Just as a side comment, I mean, NumPy now has this support for geom space, which is the equivalent thing of the NumPy log space, and then providing the logarithm here. And this just works as expected. So instead of this case here, you could rely on NumPy geom space, and there you can directly pass in the quantity min, max, and then you get back this array of quantities. Let me conclude just with some performance tips for quantities. I think when quantities have been introduced to Astropy, there was a bit of a misconception where people said like, oh, okay, quantities are going to slow down my computations a lot. And the answer there is this is not. In most cases, this is just not true, but you have to take care of a few things. And these I'm trying to show to you. So if we create a rather large array here, a 3-dimensional array with 500 times 500 times 500 entries, then you can see that if we instantiate the quantity and do this time-it operation here that we've seen already a few times, then roughly this takes 500 milliseconds for the instantiation. If we're doing it this way with the multiplication here. And this is because by default, when doing this multiplication with the unit, actually the data, so this whole data array here is copied. And this is, so it's copied under the hood, and this is what takes time. But there's an alternative way for the instantiation. So if we use u.quantity and then give in the values, and we specify copy equals false, and we do the time-it, then we'll see that actually this takes much less time. So here it only takes like 8 microseconds. So this is something to keep in mind, that statements like this do a copy of the data implicitly. And if you find somehow that quantities are a bottleneck in your computation, then this might be one of the reasons. In Astropy 3.1, there was actually a new operator introduced to avoid the copy here. So this is like this double arrow here. So you can basically assign a unit to an already existing NumPy array instead of creating a new quantity, or instead of creating and copying the data. And this is also useful to keep in mind let's say the other way around. So not for the creation of quantities, but also for if you do the conversions. So here, there you can use this little helper method called toValue. So here we just create this .quantity, and then this will avoid the copy. However, it will not avoid then, of course, like the unit transformation. I mean, this will use still this is still what you want. There are a few more details, and I've linked to the performance tips here on the Astropy page. Okay, here I've defined a set of exercises. Again, I will not go through those right now, but again, there's an easy one, there's an advanced one, and there's an expert one. And you can find the solutions to those in the attached notebook. If you have questions, really just use the Slack channel, or if you encounter any problems with the solution of the exercises, just ask in Slack. Okay, let's continue to Astropy coordinates. I think this is probably like the second most important data structure in Astropy. And this provides really like a full framework to handle positions on the sky in a way such that it becomes independent of the coordinate, or the representation becomes independent of the coordinate systems. And you can even then handle transformations between those. The core data structure for this is an object called sky coord. And you can just say from astropy.coordinates import sky coord. And one way to create this object is just to pass on to pass in the longitude and the latitude, and the coordinate frame you want the coordinates to be defined in. Of course, the good thing here is there's built-in support for quantities, so you can define the longitude with degrees with the corresponding unit, and the same for the latitude. And then in addition, you just have to define the frame. And then you can print it, and then you will see, okay, it's a sky coord object defined in the ICRS frame, so in the equatorial coordinate frame, with right ascension and declination in degrees, and this is what the values are. Again, the sky coord object can not only be instantiated with a single value, but it can be instantiated with a list, array, or quantities. Here I'm just doing an example with 2 values, so here's a list of positions. And this time I'm specifying the galactic coordinate frame. And then if we print the object, excuse me, and then if we print the object, then you can see that it's actually a list of multiple coordinates, and defined as tuples of L and B. To specify positions and the longitude and latitude angles, there are often different conventions used in astronomy, and those are all typically all supported. So you can also define the angle as an hour, minute in the HMS format, so as hour, minutes, and seconds, and degrees, minutes, and seconds. And in Astropy, this is supported just by giving the string in the correct format. Or alternatively, you can, instead of this H, M, and S, you can just use colons to separate those, and then specify the units here separately. A very convenient way to get the coordinates of an individual object is doing a query to the Sesame database. And Astropy has the built-in support for this, and as a convenience function, which is called from name. So for example, in this case, we've specified the position of the Crab nebula before. We could just say sky coord.from crab, and then it actually does the query of the database and returns the position. Of course, this requires a working internet connection. So it's not necessary. So I would not advise to use this in a script that you run for your analysis, but it's very, very handy for interactive work in a notebook. Okay, again, then I think the most useful method for the sky coord object is that you can actually transform between multiple coordinate frames. So we've defined the position of the Crab nebula in the equatorial frame, and now we can transform it to galactic coordinates. And the way to do is just by calling this transform _2 method, and then we just give galactic as a string. And then we have the position in galactic coordinates. You can quickly check by printing this object, and there it says, okay, it's galactic coordinates, and there you have L and B with the correct numbers. For convenience, you can also directly use .galactic and .icrs attributes. So instead of typing this, you can directly access just .galactic. This might be convenient in certain cases. Sometimes it can be also interesting to access the longitude and latitude values independently. And the way to do is to access position.crab.data.lon, and then you get this longitude object specified as an angle, and the same for latitude. This is just useful to know in certain situations. Okay, another very common application for sky coords is you want to compute separations between positions on the sky. And the API in the method for this in Astropy is called dot separation. So we're defining a second position on the sky here, so the position of Sagittarius A, and then we can actually compute the separation to the Crab nebula by calling position.crab.separation and then giving in the second position, and then you can see that it's like 172 degrees. Again, you could convert it to different units. So you could just, I don't know, for whatever reason, you could convert it to rad. Or you could convert it, I don't know, to arc minutes. And this is what you get. In certain cases, let's say like the inverse operation of this could be also useful. So you want to compute a new position based on a given offset from a reference position and a position angle. And this is done with a method called directional offset by. So we can compute a new position from the Crab position here by giving the separation, which is 1 degree, and the position angle. Okay, so far these were the coordinate transforms and coordinate systems defined on the sky, but there are also like another, of course, very, very common coordinate system is the horizontal one, measured in altitude and azimuth angle. And this is, of course, useful for planning observations, or if you have positions in the reference frame of the telescope, for example. This requires putting in additional information, of course, to the coordinate transformation, namely the location on Earth and the observation time. In this case, I'm using just the position of Paris. I mean, Paris still has an observatory, so it's not, or maybe half reasonable. And you can instantiate this Earth location object just by giving the latitude and the longitude position on Earth. And then you have this geodetic location object here. Right now, you don't need to know any details about this Earth location object. I think it's just sufficient to know that it works this way. And then there is this additional object in Astropy to handle time. This behaves basically like a quantity object, but a very special one dedicated for time handling. And this allows to handle multiple time formats with a much higher precision that is often needed. One convenient way to instantiate is just to call time.now, and then this will return the UTC time that is currently now. And this we can use then to define this horizontal coordinate system. And this is done using the alt-az class. And then we can actually use this to convert from the sky coordinate. So we are at the location of Paris, the observation time is now, and I want to know what's the position of the Crab. And then I can actually transform to this alt-az coordinate frame here. And this takes a little longer. But then you get back still the correct position. A side note, I think right now I don't know what the precision is that you actually get for these kind of conversions. I think in general it's rather high. As you can see, for example, it takes into account even the atmosphere, optionally temperature, relative humidity, etc. So I think you can reach a very high level of precision. Okay, to conclude this block on the sky coordinates, I've defined again 2 exercises, an easy one and an expert one. The easy one is just to define the sky coordinate for your favorite astronomical object, and work a bit with the angular separation method. And the expert one would be to make a plot of the height above the horizon for the Crab at the location of Annecy, which would have been like the actual location where the summer school would have been held. And then you can actually answer the question whether the Crab nebula would be visible tonight. Okay, let me come to the next block, which is Astropy tables. We've already seen table-like data structures before, for example, as certain D types in NumPy or as pandas data frame objects or data set objects. But Astropy provides another like simple, or actually not so simple table-like data structure, which is very handy if you want to work with table-like data. So I think the most common use case in astronomy would be, for example, a catalog. But it can be all kinds of things like, I don't know, measurement data or whatever. The way to instantiate the object is you can just instantiate it empty. And then it behaves very similar to a dictionary-like data structure in Python. And then you can start filling it with data. So what you do is you give the source name here, which is the column name, and then you can give a list of data. So here I'm just defining a few objects like Crab Nebula, Sagittarius A, Cas A, Vela Junior. And then you can define another table column like this with the longitude of the object, and then you pass in just the NumPy array or the quantity. The same here for the latitude, and then there can be other additional information, meta information, for example, like the class of the object. And this then would be a string or list of strings. If you just execute the following cell, then it gets nicely formatted in the notebook. So it gets formatted as HTML, and there you have the information. And as we've seen here, it even understood the quantity object. So it stores, in addition to the actual value, it also stores the unit and the data type. So the source name is a string, longitude is a float 64 with the unit degree. The same for the latitude here, and the source class is just again a string. Now you can use this table object to access the data in it. So you can access rows and columns. One way to check what are the actual column names, for example, what you would do with dictionary.keys, is just to access table.column names, and then you can see like which ones are actually available to access. And then individual columns can be just accessed by the name. So you can use the bracket operator here and just give the name of the longitude column here. This also works for a subset of columns. So you could give multiple column names here, like source name and longitude, and then it returns again a table object, but only containing the subset of columns. In some cases, one can use the .quantity property to access the data contained in the table as a quantity. And this is done with .quantity. There I have to do a side note. Actually, Astropy provides a second data structure, which is called a Q table. And this has improved a lot in the past years. And this Q table actually allows to store not only quantity objects, but also to store, for example, sky coord objects directly, and also just to store time objects. And this is very useful, of course, for interactive work or sometimes in scripts. The problem there is a little bit that, for example, once you want to serialize the object to disk, then not all data types that you put into this Q table are supported. But in many ways, it can be a very good choice. The API is basically compatible to the table object. But I think like the normal table object is let's say like the more stable or more safe thing to use. But in many cases, this Q table can also be a good choice. Okay, so we can access the .quantity here, and then we get back this quantity object, and we can just convert it to arbitrary units again. Then rows can be accessed just using NumPy indexing. So this behaves very similar. So we can actually slice into the table object. So we want to have the rows from 0 to index 2. And then it again just returns the table object with a subset of columns. This also works with mask, with a Boolean mask for the NumPy array. So we could do something like we create a mask by saying table source name equals crab. So we want to know what's the index of the crab object here, and this is then the selection, which is a NumPy array. So if you just check the selection object here, oops, then you can see it's a NumPy array containing just one true where the entry actually corresponds to crab. And then you can use this to index into the table, and then you just get one row back. Okay, I think there are also more sophisticated indexing schemes that I added in a small section actually to the tutorial because I thought it was useful, but we have to see whether there's time for this. And I think what's pretty important for the table data structure in Astropy is the support of serialization formats it has. There are a few very common ones. Of course, you can store a table into the common fits format. The way to do it is just to say table.write, and then you give a file name, and then it infers the format from the ending of the file name. Or you could also store, for example, in an ECSV format or CSV format. And then you can, for example, take a look at this. So here, just as a reminder, so with the exclamation mark here, you can actually execute a command line command in the notebook. So we can actually take a look at the data here. What's nice, for example, about this ECSV format is that it also stores metadata. So it does not only store the data in a CSV-like format, but it also has this additional meta information based on YAML, which stores then additional information about the data type, about the unit, and everything. I think this is actually pretty important and like a very good practice. So often you find like lots of tabular data which is poorly documented, which misses the meta information. And I think it's very nice that actually Astropy has now a way to store this along with the data, and this should like your default way of storing the data. Then of course you can read the data, the table back. And the way to do this is just to call table.read. Here I'm reading the fits version. And then you get back this table object again. There is a whole list of supported formats. And this you can see here. So there are many ASCII formats. It also supports format for pandas or pandas-like formats. Fits, HDF5, this special tabular data, IPAC, whatever. I think there was even like in the Slack, I think there was even a question about a very weird format, and I think Max managed to find like that it was actually supported by Astropy. So this is often like a good thing to start. So if you get some data, just try Astropy table.read. And then if it fails, then you just have to look for the corresponding format, whether it's supported. And in most cases, the answer will be yes. Again, similar to pandas, I mean, there are ways that you can specify delimiters and things like that, but this I'm not going to show in detail. Okay, there's a bit more advanced functionality, which is indexing and grouping of the table. So the table object implements a method which is called addIndex. And this then allows like a very pandas-like access to the data. In this little example table that I have here, I just add one index column, which is the source name column. And then I can use actually this pandas style access with the .log method, and then I can just give the name, for example, of the source, and that is defined in the source name column here, and then it returns the corresponding row. As a side note, this also works with multiple columns. Then this of course works also just with multiple keys, so you can give multiple names here, and then you get back again a table object with a subset of rows. Another thing that might be useful is grouping. You can group a table by a certain key. And this is defined with the .groupBy method. Here I'm grouping the table by source class. And then I could do, for example, just a loop over the groups of the table. So I could say for group in table grouped.groups, and then I print the subgroup of the table. And here you can see, so there's just one entry in the source class of a pulsar wind nebula, so this PWN. There are two entries for this supernova remnant, and then one for the unknown type here. And each of these group objects is again just a table object and works like exactly the same way. So this might be useful. A few other things that are useful is are probably sorting of tables. This you can just do with the table.sort method and then providing the column name. And then it will sort the table by longitude in this case. What's important to keep here in mind is that the sorting happens in place. So the actual table that you're using is modified. So it does not return a new table like table sorted, but it does the sorting in place. This is just something to keep in mind. Then there's also a method, for example, to remove a specific row by a given index. This is done with table.removeRow, might be useful in certain cases. And then you can also iterate over the table row-wise in Python loop. So you can just write for row in table and then print row source name. This helps you to write a bit more compact and more readable code. What is also useful to inspect data interactively is a method called table show in browser. And this will open a new browser window or browser tab, sorry, with some JavaScript attached. And this lets you actually search the table for given entries. So I could search for crab, or I could search for Cas or C or whatever. This is useful in certain situations for interactive inspection of data. I think the same actually exists for the notebook. So you could just say show a notebook, and then you can actually show it inline. I think this works well as long as the table is not that large. I don't know, once you have, I don't know, more than a few thousand entries, then this might get very slow. and for this case, then you, I don't know, probably better rely on external tools like Topcat or something like this. Okay, to conclude, I've defined a few exercises again. One easy one advanced one expert one, that asks you to provide an example, to read an example table and then perform some computation on it and do actually like a little analysis. Okay, let me continue with the support for FITS images in WCS. I think this is like another very common use case. To illustrate this, I'm using some example Chandra data from CAS-A. What the FITS module provides you, Astropy IO, is in general, of course, serialization of data, but I think FITS is really like the most common one, especially for image data in astronomy. And then you can just use fits.open to specify the file name as an argument. And what you will get back is an object called an HDU list. So a list of the header data units that are stored in the FITS file. If you want to know what is actually in the file, then you can use hdulist.info. And in many cases with data that you are provided with or data that you download, you have actually multiple HDUs. And then it's like a good way of looking at the data first. This one now only contains a primary HDU object. You can already guess that it's like in an image format, so the dimensions of the data is two-dimensional with these dimensions here. It's a float stored in float 32. And now we can access the data by calling the HDU or calling into the HDU list object with these brackets here, and by giving the name of the HDU. So in this case, it's primary, or alternatively, just using an index to the list. And then you can access the actual data with the image HDU that you get back here. And then you can access image HDU.data. And this, again, is a very common object. So it's just a plain NumPy array. And then, of course, you can do any operation on this that works with any NumPy array. For example, I don't know, you could use SciPy FFT convolution to smooth the data, for example, with a Gaussian or something like this. And to visualize the data, we can actually use matplotlib functionality. So we can use matplotlib.imshow and directly pass in the data as this NumPy array. There's one thing to keep in mind. By default, the NumPy array is basically switched, so we have to change the origin of the data to lower. This is the convention that is typically used. And if we do this, then you can see actually what the data looks like, and you can see a nice X-ray image of Cas-A. Then, of course, with the fits data, there's also associated meta information that is stored in the header. So if we access this image HDU here dot header, then you can see the associated information. So it says, okay, the object is Cassiopeia A. Here's the date of the observation. And then in addition, it also defines a WCS transformation. So it defines how the positions on the sky actually map to the pixel indices of this image. And Astropy then provides another class to handle this kind of information. And this is the WCS class, which is stored in this astropy.wcs submodule. And there we can just pass in the header information. So WCS, and then you just pass in the header here, and then you can print the WS, and then you can see like how is this projection defined. So in this case, it's a tangential projection with right ascension and declination. There's the center value, the reference pixel in the image. Here's the pixel size and the overall size of the data. Then there are two convenience methods or helper methods to convert between pixel coordinates and sky coordinates. So what you can do, for example, is once you have this WCS object, you can try to compute the position of the pixel 0, 0 on the sky. And this you can do just by passing in this WCS object in this little helper method sky coord from pixel. And then you get back the sky coord object. Or the other way around, we can ask what's the pixel position, for example, of Cas-A in this image. And for this, we create the sky coord object with the position of Cas-A. And then we convert this to pixel coordinates using this WCS transformation. And then we get back this array of longitude and latitude values. I think this is the basic functionality. In the exercises, you're actually asked to explore the functionality a bit more, for example, to do a cutout of the central region of the image. And then for the experts, there's the question to actually compute a radial profile of this image. I think actually we have a bit of time left, so I'm gonna show the sky images as well, and then maybe I could go back to one or two of the exercises and work on those. I think this is, again, as I've said in the beginning, I mean, it's only a subset of the functionality that Astropy provides, but I think it's like the very basic subset that you need like 80% of the time. And then there are certain situations where you then just look into the Astropy documentation to try to see how you achieve a certain thing. Okay, there's one other thing that is nice and that is often needed, and this is the plotting of sky images. And there are solutions, for example, like a Python package called ApplePy. I think this was very, very popular at a certain point. But now actually there's a more integrated solution to Matplotlib. And this is this subpackage Astropy visualization.wcs access. And this actually lets you define the WCS projection as a custom projection in the subplot of your Matplotlib plot. And the way to achieve this is actually pretty simple. So you can pass on projection equals this WCS object that we've defined for Astropy, from Astropy, and then it just creates this axis object, and then you can call imshow on this axis object, just the same way as we've done it before, again with the origin equals lower. And then if you do this, we in addition get the coordinate axis on the plot. So not only pixel coordinates, but we actually get the corresponding sky coordinates. Okay, there are a few little modifications that you can do. So, for example, often you want to define an additional grid, coordinate grid. This you can just use then using matplotlib syntax, so just x.grid. This is what you can do there. Another useful thing to know is that then to make matplotlib fully understand the coordinate transforms and the positions in sky coordinates, for certain matplotlib functions, one has to put in additional information on the transformation. And the way to do this is the following. So I'm just accessing the position of Cassie A here in ICRS coordinates, and then with right ascension and declination position here. And then in addition, I tell the scatter method that just plots the list of points here. I'm telling it, okay, you need this additional ICRS transform to plot those at the correct position. And for this, you can use x.get transform ICRS, and then it will actually plot the position here as this white marker in sky coordinates. Another thing that might be useful is, of course, you can also add circles or any shape on top of this plot. And for this, you can work with matplotlib patches. But of course, in this case, you still need to work out how to do this in sky coordinates. And one way I'm showing here. So in this case, we have to get back to the pixel coordinates and just convert the center position of class A here to pixel coordinates with WCS world to pixel. And then for the size of the circle, I can use a little helper method in Astropy WCS utils, which is called project plane pixel scales. And there I pass in the WCS object, and this will estimate an approximate size of the pixels at this position, at the center or at the reference position of the WCS. And then I can use this to convert the radius to pixel coordinates. And then I can actually define the circle object, and then I can add this patch for illustration here on the plot as well. For plotting more complex shapes, I mean, this was a little bit tedious to get this working. It still works, so this is good to know. But for example, this Astropy affiliated package for handling regions, this provides you some helper functionality to achieve the same thing with less lines of code. Okay, and then the final exercise here are just like to make a combined plot of the gender data. So there's not only a single image contained, but also multiple energy bands from the data. And the first exercise would be to plot those 1 row, 3 columns side by side. And then the advanced one would be actually to combine those into an RGB image. And that's basically the overview on Astropy. So there is some time left. I think this is good, and we could actually go into discussing a few exercises, but we could also do a first round of questions first, maybe.
Yes, thanks. Maybe one general question that was asked is that if you can merge tables like in Topcat.
Yes, you can. There are a few ways to do this. Again, I mean, a good reference is just of course, the Astropy documentation. Let me just see. I think there's a whole thing on this. So what's the? Okay, let me just come back to the notebook. I mean, there are a few things that I know about by heart. So what you can say, for example, from Astropy .table import vstack and hstack, and these are little helper methods to stack tables vertically or horizontally. Oops, I have to execute the import here. So this just takes multiple tables, and then you can specify how those tables are actually merged and joined, and what to do about metadata conflicts So this is one way to do this. Join types are either inner, exact, or outer. And then it returns the stack table as a single object. And the same for horizontal stacking, where you can, in addition, then provide. I think this was probably what the person was looking for, where you can specify a scheme for the to create unique column names if there are conflicts between the column names of the two tables.
And there's also the join method function, where you join based on two columns.
Additional information, indeed. Yeah, where you can join of the left table with the right table using the specified keys. Yeah, this is another API to achieve a similar thing.
Question from Maria: if I overlay two objects in a plot, one has its coordinates in racine and dexine, while the other one has got ratan and dectan, do I need to convert those, and how?
This is an excellent question. I think right now the subplot in Matplotlib only supports a single WCS. So in the case with the specific questions, the projection is actually a different one. I think the solution there is rather that you would, for example, if you want to plot certain coordinates, you would probably do the coordinate transform beforehand. So what you could do is, in this case, you can only specify a single transformation for this Matplotlib frame. But what you can do, of course, anytime beforehand is, you can convert the position to a different data frame, to a different coordinate frame beforehand. Like, for example, position. I think right now this is. Yeah, let's do this case here. So I could access, for example, galactic coordinates here, and then this would be the longitude, or galactic, given that my position, for example, is in galactic coordinates, and then I could specify this as galactic, and then it should still show the same position. This is one way of doing it, but there's only the possibility to handle one WCS transform per object. I think there might be the possibility in Matplotlib actually to overlay axes with different WCS objects. This might work. So what you could do is you could have your image, let's say, in a tangential projection, and then you could add an Matplotlib axis on top, which is not visible. And then you could plot or specify a different WCS axis there. I think this would be a workaround to achieve this.
Okay, maybe another one before we go to exercise. Can you handle converting position uncertainties from one coordinate to another?
I don't think that there's built-in support for this in Astropy. What just came to my mind is, there is support, for example, for velocities in GammaPy. This is something in Astropy, sorry, that I haven't shown. So in addition to handling sky coordinates, you can also handle velocities. And this is actually built on, of course, just like doing the derivative of the change, or the change of the position. And this should actually, in general, allow you also to do uncertainty handling. So actually, it might be a good feature request to Astropy to add support for this.
Good. Oh, someone can contribute.
Yeah.
Okay. Then if you want to show an exercise or go through an exercise with participants, we have some time.
Okay, excellent. So there's like 20 minutes left. I think it's probably, I mean, I won't show the expert solutions. I think this takes too much time, but we can just start from the beginning and discuss a bit the solutions to the simpler exercises. So just going back to the so where is it? Just going back to the quantities. Okay, so the first question here is like, how long does the light travel from the sun to the Earth in minutes, and how long does the light travel from the galactic center in years? Let me just open the, or actually I can also type. In this case, I can also just type it. No, let me save some time, and I'm just gonna go through the sample solutions here. So I'm opening the second notebook. So we just define the distance to the sun. There are many ways to do this. One would be just to look for the astronomical unit here and just to define it as one astronomical unit. Then we can use the speed of light as a constant, and then of course we can just say like distance to the sun divided by the speed, and then we can convert this to minutes finally. And the same for the galactic distance to the galactic center. So there we could just define it as 8 kiloparsec or whatever value you use, and then just divide by the speed of light, and then finally convert to years. And then if you execute this, then we'll find that the light travels from the sun to Earth in basically 8 minutes. And then for the distance to the galactic center, it's like, I don't know, 26,000 years. Okay, there's the second exercise was to define a new unit called the barometer. There are again a few ways actually to achieve this. So it could be achieved with an equivalency. This is one way of doing this. This is maybe something that you can try, but there's also like a very, very convenient solution. So there's, if you've checked the documentation carefully, there is a new method called def unit, and then you can actually define new units or register, let's say, like register new units to Astropy with this add enabled units. So this is like already the super cleanest solution, but there might be other ways actually to do this. The expert exercise, I think this one we leave out for now. Let's get then to the coordinates. There's like 15 minutes left. So I'm just going to show the sample solution to the coordinates. So the first one was just to define any sky coord object for your favorite astronomical object, doesn't matter, and then find the angular distance. So basically just to repeat what we've done before, but that just that you get a little bit of practice with working with coordinates. Again, there are many ways to define a coordinate. So you could, for example, choose sky coord from name. This you've seen before, and then you can just specify the name. You can specify it as a string here. This all works fine. And then you can just compute the separation here and just do it yourself again, and then compute the angular distance, in this case, from this PKS object to the Crab Nebula and the galactic center. So there's nothing new about this, and no trick, but just to make you more familiar with the different ways that you can instantiate the sky coord. Okay, the expert solution, this I'm not going to explain it in detail, but you can see or take a look at the final result here. So this then shows you actually the height above the horizon for the Crab Nebula. And then marked in this green range, this is actually the part where it is above the horizon for a given time. And then I think we could check the time and see whether it would be visible in ANOC. Just need to read the column, the labels here correctly. I think this is an old one. I have to re-execute it. Oops, I forgot the import. Just go. Forgot to execute the sale here. Okay, here we are. Okay, so this is just a need to check. This is a different time range, but this is roughly the result that you will end up with. In general, I think I've mentioned this Astropy affiliated package, which is called Astroplan, and this provides like built-in functionality for these kind of things in a very, very nice way. So if you're doing or need to do observation planning, this might be a very, very good choice. Okay, then just coming back to the exercise with the tables. The first question was just to add the additional right ascension and declination coordinates of the object. I think you know how to convert between coordinate frames right now, and you know how to add a new column to the table. So here we're just defining this table again, and then you can instantiate a sky coord object, like longitude and latitude, and then the frame here, like so. And then we can add the new columns by converting to ICRS. Just the thing that I've mentioned before. Let me just show this because it might be useful in certain situations. So you can also say from astropy.table import qtable, and this qtable object will actually allow you to store directly the sky coord object in the table. So you could just say like qt, and then you just choose the column name like position. And then you can directly set this coords table, this coords object, for example, here. You could just directly set it here as coords. Oops. And then if you show the table here, then it actually shows that this is stored as a tuple here, and you have both values stored in the same column. And then if you access this, then actually Astropy knows how to handle this and directly creates a sky coord object again. As I said, I think this is very handy for interactive use. The same goes for quantity and time objects, not only sky coord position and sky coord objects. But there might be problems in the serialization. I think there is, by now the serialization support has improved. I think one can actually write this thing to an ECSV file. CSV, I think this should work. But this is not guaranteed to work for all formats, and also not for all data classes that you can store in this table. But by now, I think the support has improved a lot. Okay, then there was the exercise to actually load this Fermi 2FHL catalog. So it's an example catalog of high energy sources measured by the Fermi-Lat satellite. And this you can just read using table read.fits. In this case, the table is stored in the second HDU. And so you have this additional possibility to tell table.read like which HDU of the fits files you want to read. And then the first question was to find the brightest source of the table. And in this case, you could check, for example, where's the flux stored of this object. And in this case, it's called flux 50. And then you could, for example, just sort by the flux values and then access the latest or the last row of the sorted table, and then access the association column here. I think this is something that should just work. Then the second thing was second exercise was to find all objects within a given radius. And one way of achieving is that you just manually read the longitude and latitude values columns of the table, specify the coordinate frame, and then find the position of the crab, either manually, or you could add an index to the table, and then you compute the separation of all those coordinates, and then you make a cut on the maximum separation, and this is then what you should end up with. Again, you can take some time to go through the solution in detail and also to try it yourself, and then ask in the Slack if you have any questions. There's one, the expert solution, I think I could leave out again. This will ask you to make a nice plot of the data contained in this table, sorted by source class. And again, one could just rely to do it manually or to rely on this grouping functionality of Astropy. This works as well. And then you get like an all-sky plot of all the objects stored in the catalog, separated by source class, and then marked with a certain color. Then another question on the fits images in WCS was just to read the other data images and then make a combined image just by summing all the data across all energy bands. The trick here is just to write a Python loop. I think you've probably done this multiple times. And then you could just store everything in a list and then sum across this list using NumPy, and then finally showing the summed data. Or you can even directly use WCS axis here and make this plot a little bit nicer. Then there's this advanced question of like making a cutout of the central region of the image. And they've put a link. This I haven't demonstrated in detail, but there's a little helper class called astropy ndata.cutout2d, which helps you with this. And then another question was to find the sky position of the brightest pixel in this cutout data. And they've given a few hints, like how you can use NumPy argmax or NumPy unravel index to do this. And then if you do this this way, so this cutout takes the additional WCS information, you can define the center as a sky coordinate. Then you could use this argmax to get a flattened index. And then you can use unravel index to get the pixel coordinates and then transform it back to a sky chord. I don't want to explain it here in full detail, I think, because probably most participants didn't have the time yet to actually solve the exercises, but this will give you a little bit of guidance. Then there's this expert solution or expert exercise on the radial profile. And there you could rely a bit on NumPy broadcasting and things like that, just to repeat this a bit from Wednesday. Then let's just because it's nice, let's go to the plotting of sky images. So the first one was just to make this combined plot of the Chandra data for all energy bands side by side. Again, you can just read the data in a loop. You can specify this WCS transformation to work with WCS axis of matplotlib. Then you can call it imshow, and then you can also choose a nice title for this and make your plot in energy bands. This is roughly what it could look like. And then there's this advanced solution of combining those three energy bands into an RGB image of Chandra data in different energy bands. And there, the question is a bit like how to renormalize the data in between. And this is done just by dividing through the maximum of the data in each RGB band. And then you can use matplotlib imshow to put in three images at the same time, and imshow will actually understand to make an RGB image out of this. And if you do this, then it will roughly look like this, and you'll end up with this beautiful RGB image of the Cas A supernova remnant. I think that's it. So this was just a brief walkthrough through the solutions. I think there's probably some or still enough possibility that you can work on it yourself. I've just given a few hints here. If you encounter any problems or questions, again, just ask in the Slack. And I think there's maybe a final, or time for final round of questions. And I will leave you with this image here. I think it's nice.
Thanks again. There is only one question since the first one. Is it possible to format the text on the tables using specific criteria, such as putting the maximum values on the column in green italic font?
This is again, a very good question. I think this specific formatting that the person's asked for is not possible. However, what you can do, and this is also very useful in certain situations. Let me just go back to this example table, the one that I've used here. Let's just use this one. So this is the example table here. What you can do is for each column of the table, you can specify the format. And for this, you can just use like normal Python formatting. So you could just say, I want to have this in exponential format with a certain number of with a certain number of digits after the comma. I don't know, like 3e, something like this. And then if you plot this, okay, in this case, oops, sorry, not table format, but table, sorry, for a given column. Or maybe let's just use 3f in this case. And then you can see that it actually adjusts the formatting when you print out the table. And this is also valid, I think, for serialization. And this you can specify for each column. And there's maybe a more convenient way to do it for the whole table at once. I think this is something that is useful. As I said, I think for the font things, I think this is probably hard to achieve. Only, I don't know, if you have a way, I don't know, of hacking into the HTML representation of the table or something like this. But this is probably a more common thing to do.
Yeah, thanks. I think that answers a part of the question at least, and for the color of the font, Max is replying in the Slack.
Mm-hmm.
Okay, well, I don't see any other question. So thank you very much again. We are right on time. And so we see each other this afternoon at 2 p.m. for the seminar on artificial intelligence for cosmology. So yeah, thanks and see you.
Thanks, bye.